Oops. All right. Is that visible?
Yep.
All right, cool. So I guess just a little background. While I was growing up, I did a lot of music production in software, and I was using synthesizers to just learn about music and how sound was produced. And I had a vector scope open one day on a specific synthesizer, and it had this phenomenon called stereo detune, where when you raise the slider or the knob on the stereo detune, it would pitch one ear up in pitch and the other ear down. And it started creating these shapes in 3D with each frequency that you added in. So yeah, I'll just quickly demonstrate, and I'll probably have to mute it. It gets pretty loud. Yeah. So yeah, this is just a vector scope over here. I'll switch over to lines first. And you can put in whatever frequency you want. These are the upper bound and lower bounds. It can go into the negative too. So yeah, this is the frequency select, the fine tune, and the phase, which the phase, this is the special sauce. It will basically rotate the image in vector space by shifting. It's the same frequency, but it shifts the right ear forward a little bit and the left ear backward a little bit in phase. So it's the same frequency, they're just phase shifted a little bit away from each other in each ear, and it's always equal and opposite. And as you scrub through the phase, you can see it rotates the coin here, but it gets rather interesting as you add more oscillators or dimensions to this. You'll quickly see toroidal shapes starting to pop out as you pull the phase of the other oscillator. And all the harmonics, the reason I call it a harmonoscope is because it's pretty easy to visualize each harmonic in a visual way, as well as audio. You can also hear this going on, but I muted it for right now. So a couple of interesting things I noticed while playing around with this is, you know, obviously like sacred geometry popping out everywhere. And there's a few isomorphisms between space here. For example, volume seems to be related to scale. And phase seems to be related to rotation. And you can, you know, look at these shapes from any angle, really. So as I kept playing with this, I found a neat fact about it recently, actually, which I found all the basic shapes, essentially. Let's see. So do 2.5 and 7.5 over here. So as you'll notice, I turn the volume down to this. We'll see the triangle, right? And that's the first harmonic or the octave from the fundamental. And then you can increase it, the third harmonic, and you get the square, the fourth, the, what is it, pentagon, etc., all the way up 5, 6, 7, 8. And you kind of have to pull the volume down in relation to the frequency to really see the fundamental shape. But what's really fascinating here is, like, there's so many angles to these shapes. You know, from this angle, we see the, what is it, hexagon, I think, here. But from the other angle, you know, you get flowers, petals. And they, you know, you can mix them together to points where they, well, it's clipping right now, so it's hitting the edges, but you can scale these up and down and rotate them all around and just really see all these relationships in frequencies that weren't really visible before. And this, just goes on forever, all the way up the harmonic progression. And each time you kind of settle in on one of these stable nodes is when you know you're at a harmonic, a really stable harmonic. And then something else that popped out when I was demonstrating this to Gary was there's fractional harmonics as well, like 150 to 100. And you get, this shape, which you can rotate again to like the opposite end here, and you'll get, there's the star. Let's see, I think 175 was another one. Yeah, so then that's, I don't even know what to call that. But yeah, so that's really the basics.
Actually, Nate, maybe if you could whiteboard the basic circuit diagram,
Sure, yeah, totally.
that might.
Let me, oh, can I annotate it right here? Oh, cool. Can you guys see that annotation on my screen?
Yep.
Yes.
All right, cool. Let me grab my pen here. Okay, so, okay. So yeah, what's going on here is basically, so yeah, oscillator 0 and oscillator 2, they have, just a single frequency being output, but it's split into dual channel left and right for each oscillator. And on these split paths, there are little phase shift nodes, right? And these phase shift nodes go in equal and opposite directions. So same frequency for each channel, but different phase relationship between the channel. And then what happens is it converges onto the speakers, right? The little speakers here. These are combined, basically. The left signal go to the left speaker, and the right signals go to the right speaker. And that's basically it. That's all that's going on here. It's a little more complicated because the vector scope involved is performing a fast Fourier transform and pulling the frequencies out so I can plot them. But yeah, other than that, this is basically, what's going on.
And what's interesting was I'm starting to do like the same thing from an analog perspective with an oscilloscope. Right? So if you have a signal generator or any kind of source, I'm starting to build up the analog version of this that you can see in an oscilloscope that has the same characteristics. It may not be as powerful as some of the features that Nate has, but it shows the same sort of behavior.
Yeah, I'm a little more
Yeah,
free in the.
someone had a question, Bonnie?
Yes, following on to what you just said, Gary, Nate, this looks to me like you've really turned in Lissajous figures in the oscilloscope into an omnidirectional path versus, a linear path, because I haven't seen these with the oscilloscope or Lissajous figures anywhere.
Right.
Could you talk a little bit about that?
Yeah, so essentially when I first discovered this, right, I was digging into the internet like, what is this? Who has done this before? Couldn't find anything, right? But I found a lot of concepts related, like the Lissajous figures, Rhodonia curves, hypotrochoids, epitrochoids, all these different, even basic shapes, triangle, square, all that was just popping out of this thing. But yeah, so I dug into Lissajous really hard because I noticed like definitely the most related there, because I think, yeah, the Lysigis figures were initially invented in an analog fashion with a pendulum, if I'm not mistaken. Yeah,
Yeah.
and so yeah, it's funny enough, you can get these shapes from pendulums if you set it up properly, and also like I've seen people do it with mirrors and lasers, but most people just bounce the light off one mirror. I think to get this, you'd have to bounce it off one and then another with two speakers. Yeah, but yeah, definitely super related to Lysigis curves, etc. But
Yeah,
It's
well, I
close
thought,
to the
go ahead.
Lysigis orbits.
yeah, okay, so I can actually demonstrate an orbit here. Let's see. If you go low enough frequency, and actually let me turn dots on because dots are a little more fun. And I actually discovered something else about light with this. Well, let's see. Let's go to 5. Yeah, so I think there's a trail here too. I can turn it on. Yeah. So I can trace out the shape. And yeah, there's an orbit right there. And you can rotate the orbit and look at it from different angles and, pull the volume down to really down there, something more physically real. And I mean, I get, so if you turn off this oscillator, you get, I don't know, let's say a planet orbiting a sun. And then you turn on this oscillator, you might get the moon orbiting the planet. And then you can keep going. You can add an oscillator, you can pull the frequency up to something crazy and turn down the volume a little bit. And then you have a spiral on a spiral on a spiral, right? And this just keeps going and going. You can stack it.
Yeah, Bo, you had a question?
Yeah, I wanted to ask you, where does the third oscillator fit on your diagram that you sketched?
Good question. Yeah, it would just be another, let's see, just one more, F prime, and same thing here, splits, same exact pattern, couple phase shifters, left channel into the left, right channel into the right.
Okay.
And you could just keep stacking them up like that.
And how many had you stacked up ever?
That's a good question. I don't remember, honestly. I've sat in front of this tool for hours on end, just seeing what's buried within. Probably a dozen, maybe, because I don't know, after 4, it gets really hard to track what's going on.
How many pixels of a screen can you project that to?
It's all vector, right? So whatever size, doesn't matter. You can scale it up, down, any size really.
Is this software that you created?
Yeah, well, these are known, like the generators, the oscillators, right? That's kind of provided for me from the web browser. It has like an API to generate sound, much like libraries in C and C++. So yeah, I reverse engineered the synthesizer that I discovered this from, and then built it into a web app.
And,
So-
and Nate, this is something that you could share with anyone and they could run this themselves.
Yeah, it's hosted here. I'll give you guys the link after I'm done here, and you can play with it all you want. But yeah, it gets pretty great fun. A lot of very interesting patterns, and
Yeah, go ahead, Joe. I think Joe had a question.
Yes, have you compared these to the semantics diagram?
I'm not sure what that is.
Okay, a number of, well, there are several ways that they demonstrate the semantic diagram. That's where you take a metal plate and you put it on top of a speaker, and then you put
Yeah.
sound through it and you get the patterns.
Yep, the Chladni plates and like cymatics and stuff.
Yeah, and some of it's done by water, some of it, there's a variety of ways that are done that way.
Yeah, so I did it with water, and I found the same patterns popping out of the bowl of water. It was really fascinating to see that, but really hard. You have to really get the right angle. You have to
Yeah.
light shine down and see it from that angle. But yeah, the patterns are totally there. And what I started to realize is there's almost certainly a way to say if I have the frequency and I have the glyph, the cymatic that appears, I can probably predict the radius of the bowl or the size, the dimensions of the bowl. And likewise, if I had the size of the bowl and the frequency, I can probably predict the cymatic glyph that appears. And algebraic.
Yeah, are you familiar with John Reed's work?
I think so.
He's developed what he calls the Harmonoscope.
Harmonoscope.
Yeah, the Harmonoscope, and basically he's now he's looking at it in a biological standpoint. He's looking at viruses and cell structure and that type of thing by using sound and using the sound wave to give the pattern. And I'm wondering if since you're working with being able to observe three-dimensional patterns, which most of the patterns in the past have been studied as almost as two-dimensional elements.
Right.
And when you look at oscilloscopes, you think of it as 2D, but in reality, you're getting that third dimension that you're working with. And what I find fascinating is the fact that very few people have looked at it from a visual standpoint of generating three-dimensional views. And by your introducing motion into the system, you get the impression of 3D.
Right.
Which is wonderful. But one of the questions I've had is, have you looked at that as trying to generate, let's say, a stereographic image to where you would see them in 3D?
So, not quite. I mean, I guess I would call this a stereoscopic projection because I'm utilizing two channels.
Yeah.
And then, phase shifting them. So it's kind of the same way like 3D glasses work. It phase shifts the light just a little bit, right? But no, I haven't dug too deeply into anything beyond just this software.
Yeah, I think Joe's referring to having a second image that you stare at.
Yeah, well, that's what he's saying.
Your eyes. So it'd be a second image with an adjustment of your point of view.
Right. Yeah. We could probably, I wouldn't be hard to add a second box here and
a little phase shift in it.
And do a phase shift. Yeah, that's a good idea.
And in fact, I don't think it's limited to 3 dimensions, right? In reality, I think you can project 4 dimensions if anyone can even imagine what 4 dimensions look like. But
well, let me show
you.
you.
He's already added the third dimension, and that's motion.
Yeah, here I can show.
Okay, so now the fourth dimension would be the stereographic. I mean, that's the way I put them. I put them in that order because when you start dealing with matter and electromagnetic fields, you're primarily, when those come together, you've got the fourth dimension.
Okay, yeah.
So I like your wonderful patterns that you're starting to occur there, because I could just see where they could, really give you a much better feeling of what is actually how the sound travels through a medium.
Right.
What does it really look like when it's passing through water, or when it's passing through the air, or some other gas or liquid or something like that?
Right.
What is that form and structure that's really sound waves are creating?
Right. Yes. Yeah. I'm with that line of thought, definitely.
Have you applied this to a musical instrument yet?
Well, I mean, I discovered it from a musical instrument, so
right.
but I don't know, I haven't figured out how to apply it to other instruments. But I did kind of realize something in the development of this. A lot of our instruments are linear low on the left, high on the right.
Mhm.
And they all kind of follow this pattern. But what I started picking up on is the frequency domain doesn't really work like that. It can go both ways, right? You can go negative if you want and positive. And I started envisioning instruments that instead of low, high, or low, left, right, high, it would be fundamental in the center and then increasing frequencies outward from that. I've toyed around with this concept a little bit, but not too much. But if anyone is a musician or has a piano, and you plot the harmonic progression on the piano, and then you flip it over the axis of the fundamental you chose, you get mode translation. So I think in the the first octave, you'll have your triad, your third. The second octave introduces the fifth on the third. The third octave introduces the seventh on the fifth and the third, and the fourth octave, right? So on. And eventually, I think it's the fourth or fifth octave contains our 12-tone chromatic scale of the harmonic progression. It's not perfect, right? But it's very clear. And as you plot that out and then flip it over on its axis to the other side of the piano, you'll get different modes. So on the right, it's the Ionian, the major scale, right? If you plot out the harmonic progression, it's pretty Ionian. You flip it over, you're going to see the Phrygian scale, just right there, pops right out. And you'll also get, your minor third. Basically, the reflection is the minor, or Aeolian, I think, right? And then, yeah. So the right side, if you plot it harmonically in major scale, you flip it, you're going to get minor scale stuff, minor thirds, minor fifths, etc. Pretty fascinating side track there, but yeah.
I think Bo had a question.
Yes, I was just wondering if you had ever considered the electronic idea of modulation, or even radio, where you have a audio frequency, and then you have the radio frequency, and then you have the intermediate frequency as a result of mixing, and also which is used to detect the signal and break it down back to audio. Have you ever taken that consideration into the schematic that you drew before? It looks like there is actually modulation going on because you're mixing two different frequencies, and
Right.
one frequency is considerably more than the other.
Right. I haven't actually, no. That's a good question. I'll have to pick your brain on that. Yeah, not really. It's mostly just been digital.
Now, if you look at your, yeah, I think you're right, Bo, is that what the diagram that Nate showed earlier kind of simplified the results, but when you're mixing signals together, you're actually getting the sum and differences as well, right? So
Right.
you get the first two frequencies plus the sum and the difference. So you got 4 frequency components.
So
that-
did you ever sort out how to display those different components? That's what I'm getting at too.
I could probably, I could chart them out linearly, but I don't know
With a
how
filter,
I
you
would
could probably-
display it.
You could probably filter them out maybe, or
Yeah, well, yeah. I could, I could catch it right before it goes to the vector scope, right before it's all summed together. Yeah, I could, before they're summed, I could analyze it and then plot it somewhere here. So yeah, we could see the oscilloscope type waves next to this, if that's what you're getting at.
Yeah.
Yeah, I could definitely add that in.
Yeah, the way it goes into a 3D simulation, that I think that's more of a simulation and not necessarily actual 3D in terms of the academic, mathematics behind 3D. So
Yeah.
it is fascinating. It does it just like Cymatic does it with the plate that you vibrate, and what else they do, ferrofluids. That's even more amazing. But these are all just I don't know, they're similes, they're analogies, they're not really the real thing. But I think it's a fascinating part of nature, that nature has this sort of crossover. We think this is 3D, but it's actually not 3D.
Right. Yep.
It's 3D sound, yes, but it's not 3D in the way that geometry talks about it.
Right. Yeah, totally. Something else I noticed last year is I added light to the simulation on accident. If you'll notice, I'm going to bob it up and down. It's going in between two.
Yeah.
Let's see. Yeah, there we go. So the light is also an oscillator, and it's just in harmony with the geometry that's there. And I'm not sure if anyone's done 3D work, but there's a thing called the inverse square fall off, which we've been using in 3D engines to get a very realistic light spread on objects. And so I have a game development background, and I currently do virtual reality development right now. And so personally, I'm seeing some very similar fall off from the way I implemented light. And let's see if I think one of these rotates the light. Yeah, you can rotate the light in any direction you want, really. And you can see it comes into the light and goes out of it. And it doesn't matter what shape you have, it'll still be going, it'll still fall perfectly onto it.
So is that kind of like the modulation of the light intensity of each dot?
Yeah. Yep.
And where is that modulation coming from? You said it was accidental, or something you control?
It was, well, yeah, I was just playing with the vector scope output, trying to see what I could find. And I literally accidentally applied the frequencies of this output, the sum of the output, right? The light followed that. So, as these dots are being drawn and they're swung around, it's basically, it's correlating 1-to-1. It's hitting these pixels should be brighter. It's hitting those pixels, they should be darker, based on the frequencies and geometries at play. Yeah, so, and I don't know how to explain this really. It's kind of crazy.
But yeah, there's a lot of interesting uses, I think, for this.
Nate, you are showing us, but is the sound also, can you play the sound of this as it's changing?
Yeah, I'm not sure if you can hear that.
Yeah, I can hear. Yeah.
Well, that's really helpful to hear the sound.
Yeah. Yeah, it goes back to Johann Kepler and his idea of these nested, the orbits around the sun of the different
Exactly.
planets. Have you charted or written a piece about how this fits into the history of using frequency to visualizing frequency and sound at the same time?
I have not, but definitely has been on my mind. Yeah.
Even Wolf from Demonstrations Project only has a cubic way of showing the three-dimensional Lissajous figures, and that you can interact with. But this is such a big leap that putting it in a historical context would really put it into a better understanding of exactly what you're doing and how it could be used.
Totally. Yeah, I agree there fully. It's on my to-do list.
Well, it's very Pythagorean, and it's very ancient what you're doing, but with new tools, new technologies, because
Right.
we've always dealt with frequency and sound. But when Bucky was writing his omnidirectional halo piece, which is one of his best pieces from the early days in the 40s, and when he was writing that, he was taking sound and thinking about it visually as, you know, this series of nested environments. And that's how he moved to frequency with geodesics. Joe can correct me on this if I am wrong, but that's where I see this big leap is very much like Bucky's big leap that led to geodesic frequency, different frequencies of domes, and thinking about the omni-triangulation of the sphere versus focusing on the cube.
Right. Yeah, totally.
This could be like a 21st century harmonograph, right?
Right.
Like that's the pendulum, and then the bed spinning, you know, rocking at a different
Exactly.
rate.
Yeah. Totally. Yeah. I guess I pretty much covered everything that I know of, at least in this tool, other than continuing to add dimensions here. And yeah, you can get some pretty insane geometries.
Nate, on another track, when you do your diagram, you have clockwise and counterclockwise, or an oscillation going left to right and right to left. And so it's the interaction of those two that produce the wave harmonics. Is that correct in your view?
Right.
Okay.
Yeah.
What if you had the right left, let's call it, interaction, but you could only see the right? What can you make that form visible?
It's a good question.
Because I think this gets to the heart of why in our world we perceive only one-handedness. We don't perceive the anti-wave. We see the real wave, so to speak.
Right.
And but the anti-wave is there. Without it, there would be no world. There would be no experience. There would be no wave.
Right. Yeah. I don't think I could do it as the tool is right now, but I can add that in to isolate channels for sure.
Okay, good.
Yeah.
Now, I would really be interested in taking a look at form done that way. For my work, that would really be helpful.
Cool. Can do. Yeah. Man, I don't know if you guys can hear it, but as I shift the phase, at least in my room, I'm getting, you know, full 3D interference here.
Actually, we're barely hearing that. I'm not sure if it's just volume on your side or.
Yeah, it might actually just be coming through my microphone and not actually sharing the audio.
I don't hear it.
Yeah.
Yeah. Well, yeah, I'll send a link to this and y'all can play with it to your heart's content.
Nate, have you put videos or written up kind of papers, as it were, or such on this? This is really some amazing. I'm going to have to chew on this for a long time just to get the different components. This is wonderful.
Yeah, I haven't, unfortunately. I haven't. Well, I don't have a hugely strong background in analytical thinking and mathematics and such, and categorizing and stuff like that. This was mostly just intuitively gathered from the space around me, just having fun, really exploring. But definitely I've had a huge yearning to write something about this. I'm just not sure where to start because there's a lot. But I think Bonnie's suggestion is a good idea, a good place to start. Start from the history, right? In time, just go back in time and start there, and then carry it forward, and maybe, yeah, I'll begin to be able to organize my thoughts because it's very nonlinear.
If you create the context and differentiate what you're doing, so anybody can see quite quickly the difference, what you're doing that's absolutely new with the vector scope, or what did you call it?
Harmonoscope.
Harmonoscope, yes.
Yeah.
And so, but really situating it, and this is what I always tried to do with Bucky, situating something really innovative into a longer history of big leaps that were made. I have just one more question about the chirality and helical. This is kind of like what Don was asking about the chiral potential to do something that's less symmetrical and more. Have you been able to do something that's really like in the tetrahelix, where you see this nest, you can nest structures, but they twist and turn and have relationships to chiral versions of each other?
Perhaps. I don't know. Maybe as you keep exploring these frequencies, you do run into some different things, like jitterbuggy kind of things, kind of like right here, it's kind of jitterbugging a little bit, right?
Yeah, yeah. That's
So,
where
yeah.
it gets out of the spirograph, or, you know, which we all grew up with, out of that super symmetrical aspect of seeing harmonics into something really, really different.
Right. Yeah. I've generated some very different shapes here. It would take me a while to find them again because, you know, they're buried deep in the harmonic progression, but it's all about stacking harmonics on top of each other. And then what does that jitterbug effect actually is detune, right? Just ever so slightly away from the harmonics you've stacked up. So right now, like, I'll put this back in harmony and I'll kind of just stay still in stillness. But then you start going out of harmony, you get the jitterbugging kind of effect. And yeah, so it's sort of related there, I think.
Very cool.
I hope you're considering making a directory and walkthrough from the very basics to each of these benchmark points and the reasoning behind them that you've discovered.
Yeah.
Because this is wonderful.
Yeah, definitely. Again, on my to-do, but organizing these thoughts is hard. That's so abstract.
I'd like to contribute to you doing that, meaning like I
Yeah.
can give you some historical framework. If you want.
Absolutely. Yeah, I would love all the help I could get to get this information out of my head because it's stuck in there right now.
I'd love to sit down with you sometime and maybe do a recorded Zoom where I could ask you questions that will seem embarrassingly basic. Because
Yeah.
I like the segue of how do you get from, you know, what I'm seeing to why am I seeing it?
Right. Yeah, totally. I'm so down for that.
What about the, okay, so you talked about the 12-tone scale. So can you show the difference between the pentatonic scale and the diatonic scale and the 12-tone scale, the chromatic scale?
Probably actually, right? Like plot the frequencies and see how it pops up. It would probably take me a while to plot all that out. And there's only like 5 minutes left here, but
Sure.
I will do that.
I think it's really important because most people don't know that there's 3 different ones or how different they are in terms of where they came from. Like gamelan in Southeast Asia is using the pentatonic scale, and it's the 5-tone scale. And you know, you can really show that, and anybody going into music would understand the differences.
Right. Yeah. Yeah. It really reflects just that underlying progression to all of our music systems.
Yeah.
Yeah, definitely.
Actually, Bo, I thought you had a question.
Oh, yeah, I got 100 questions, but keep changing every 2 minutes. Right now I'm wondering, did you ever plot, what do you call it, chords? You know, I remember when I was trying to learn guitar, you had to play chords, you know. Do you ever do that to see what it looks like?
Technically, this is a chord, right? 100 hertz, 1,818 hertz, and 1,310 hertz. So that's three-piece chord right there.
Yeah, I'm not that smart about chords, so that's a chord, great.
Yeah.
Did you ever play with that so-called 528 frequency?
A little bit. Well, for this tool at least, this tool is all about relativity, right? So as a demonstration, let me simplify this a little bit back to the toroid.
Right, well, what I meant is, for instance, you're showing a chord, and I assume that you're saying you're often showing chords. Now, would you take the chords of a 528 versus the 440?
Ah, okay. That's a good idea, right? I haven't done that. That's a really good idea, because then it would act like an interferometer,
Yeah.
right? Yeah,
Musical.
totally. That's a great idea. Awesome. I'm gonna write some of these down before I forget.
Well, they got it recorded anyway. I suppose it's
Oh.
going to be available, right?
Perfect.
Yeah, that's right.
All right, awesome. I'll run over the video again, and I'll collect all your ideas, and I'll try to hash them out into the tool.
That's awesome.
I don't know if this is relevant at all, but this kind of came up on my feed in the last couple of days about a metamaterial that they came up with that can redirect sound waves with little or no loss.
Yeah.
They say it's not the material so much as the shape, which of course makes sense.
Right.
But there's these little yellow channels, little tubes, as it were. And I was wondering, boy, it would be interesting to set those up in a circle and somehow be able to transmit through that cycle. I don't know. That's as far as my idea goes, whether it has, resonance.
Yeah, no, I've been seeing those articles pop up too.
It looks credible.
I think you're right. I think we can probably find some analogies there for sure.
Are you developing shortcuts to set up your channels, or what do you call them? In other words, you get familiar with using certain chords or what have you. You have a shortcut, like a keyboard shortcut or a mouse thing that you click on that'll immediately put you into where you were yesterday at 5 o'clock, or something like that.
Exactly. Yeah. Yeah. Sort
And
of.
can you quickly save the settings?
Yes.
And label them as a file?
Yeah, totally. I don't have it enabled right now. I was changing some of the tool when I broke that part of it, but yeah, very easy to save profiles and presets. I had that working in a previous version, but yeah, I'll get that back up and working.
Well, Nate, if you if you're willing and you want to join us, in subsequent weeks, I'm sure we can have a lot more to discuss.
Yeah, totally.
Great.
Yeah. Looks like it's 8, and if there's no more questions, I'm good.
Wow. Thank
All
you.
right.
Thank you, Nate.
Very nice.
You, Nate.
Thank you.
Wow.